So we left off last time looking at combinations of logic gates to get different kinds of gates, realizing the NAND was the universal because we could build anything from that. And we want to expand our studies into coming up with min-term expressions, max-term expressions. Then today we'll look at Boolean algebra, which probably won't be that much fun, but then we can supersede that with a Carnot map, which really is a lot of fun, I think. So that's where we're headed. Let me start out with a truth table here. Let's say I have a 3 input. So I have a C, B, and A. And I get that, yeah. And our output would be, I guess we'll say this is Y. Usually we use that symbol for the output. I'm going to have 0, 1, 0, 0, 0, 0, 0, and 1. Okay. And I'm going to look at where I have the ones on this. I'm going to look at this one. And I'm going to look at this one. And I'm going to write the min-term expression, which sometimes we will call the sum of products. If I look at the zeros, I'll look at the max term expression, but when I look at the min-term expression, I'm going to look at the highs on the output. So this is to say that, let's see, C is a 0, so that would be saying not C. And B is a 0, so not B. And A, or, because A, I don't invert A because it's a 1. And then down here, let's see, they're all 1s, so I would just say C and B and A, right? So I could put these two together and come up with the expression C and B and A, or, because it's a sum of products, or not C and not B and A is equal to our output. Okay. And a lot of times we would write this as CBA or not C, not B, A is equal to Y. Okay. But you can see the sum of products there because our AND is the, looks like the multiplication symbol and our OR is the addition symbol. So this is the expression that we would have. Let's see if we could build that thing. What's that going to look like? I'm going to have some 3 inputs. Let's say I have at my disposal 3 input gates. So I could say that I have A, B, C here. What's that? We may be able to, yeah. I mean, we're going to talk eventually about taking that expression and trying to simplify it for sure. I'm not going to worry about simplifying that one. But, yeah, let's see. Oh, we could put a Carnot map on it a little bit. And I'll need another 3 inputs, so I'm going to say that this is A, B, and C. Take another 3 input AND gate. Two input OR gate. There's our output. And what do we have on this one? A was straight up the same. And then B, I needed an inverter. And C, I needed an inverter. So we got something like that. So let's say I look at the this first one here. If I do this one, I'm not going to go through and check all of these, but if I do that one, does it work out? So C goes in as a 0, B goes in as a 0, and A goes in as a 1. So I'm going to end up with a 1, 0, 0. And then down here, I'm going to end up with a 0. No, I'm I'm going to end up with a 1. And then I invert this one, so I get a 1, and I invert that one, and I get a 1. So if I, here I'm going to have a 0, here I'm going to have a 1, and of course I get a 1 out of this, right? Okay. So maybe I'll try a little bit different color here so it shows up. I don't know, do we get red showing up pretty well there? What if I want to do this one with red? Does that red show up in there? Oh, a little bit. I guess you recognize it's a much thinner line. So if I look at this one, what is C? It's 0. And B is 1. And A is 0. So that means I would have 0 here, I would have 1 here, I'd have 0 here, so I would again get a 0 out. Then down here I would have a 0. I invert this 1 and get a 0. I invert this 0 and get a 1, and we still get a 0 out. We'll have a 0 here. So for these two, at least the first two, it appears to work, doesn't it? Okay, and I could leave you to go through all the cases. I'm not going to belabor that, but it looks like that worked. So we were able to go from the min-term expression to the circuit. What if I had maybe a different truth table? So let's say that So let's say it's something like that. Now if I wanted to come up with the min-term for this, it's probably a little easier to remember sum of products. So I'm going to be looking at the ones here. So what am I going to get out of this thing? What's this going to be? If I look at the first one, I have not C and B and A, or then looking at the second one, what's the one that I have to invert? A, so I'll have C and B and not A is equal to our output. So if I build a circuit on that, what's that look like? Again, we'll start out with some 3-input AND gates. And so we've got A and B, and then not C. Okay, so that's A, B, and not C. And then what's the other one? I want to do not A. There's not A. And then B. And finally C. We're going to OR these together. We have something like that. And you could go through and build that and test it if you wanted to. Questions with that? Going from a min-term expression to a circuit. The question might come up, well, what about these zeros? Could we look at the zeros? It's probably not going to be advantageous in these cases, but maybe we have a circuit with a whole bunch of ones, and we're going to get a lot of terms out of it. Maybe we'd like to look at the zeros. So is there something that looks at the zeros? And we can do that for sure. So let's try talking about min-term and max-term expressions. So we'll do that with a bit of an example. So say I look at B and A. This is, of course, our inputs and our outputs. Okay, so if I wanted to look at the min-term expression, I'd have to look at these ones, wouldn't I? So your min-term is going to look something like this. Not B and A, or not or B and not A, or B and A. Is that right? Okay. So that's your min-term expression. If we look at our max term expression, so let me come over here and talk about max term. We haven't talked about that yet. Max term, which is going to be product of sums. Product of sums. Remember, min term was sum of products. So the max term is product of sums. We're going to look at the zeros, and because that's a 0 and that's a 0, I can just say that I have B or A is equal to Y. Now if I had multiple terms, I would AND them together. So in this case, writing the max term expression is quite a bit shorter than the min term expression.
Why is it B or A if the output is 0 when you put them or not?
Well, we're looking at zeros. With the min term,
0 as an output?
right. Well, zeros as inputs and zeros as outputs. Okay. So if I had a 1 here, then I would have to invert it. So
since it's the same as the input.
Right. Okay. Yes.
So the max term is obviously easier. When you put it all together, will it still get the same exact?
Yeah. This would be a lot more difficult. I mean, we built this. We're going to have what? 2 inverters. We're going to have 3 2-input AND gates and a 3-input OR gate. Here we really have just what? An OR gate. Yeah, just an OR gate. Which this really is a truth table for what? OR. It should not surprise us, should it? So this is kind of a quick and easy first example, but let's try one that's quite a bit more complicated so we can see some of these getting longer terms. So let's see, we've got this. So there's our input, here's our output. And let's see, we had a 1, a 1, a 0, a 1, a 0, a 1, 0, and a 1. Okay. And normally we'll probably, the min-term expression is probably going to be, we're going to use a lot more because we can go right to the Carnot map with a min-term expression. But let's, for practice, let's come up with the min-term expression and the max-term expression. So if I want to talk about the min-term, let's see what that is, and the max term. Let's see what that is. So if I'm looking at the min term, I'm looking at what? The ones, aren't I? So this one, this one, this one, this one, and that one. So what are we going to end up for the min term? Not C, not B, not A, or, that was the first one, then not C, not B, and A. That should be the second one. We get down here, not C, and then B and A, or not C, there's B and A. And remember, these really have ands in between them, don't they? I've just omitted that for speed and ease, which is pretty common. Or, so we'll be looking at this one where we just have not B, don't we? C, not B, and A. And again, we could put those ands in there if you wanted to. And the last one we would have would be this one, just CBA. Okay. So we had 1, 2, 3, 4, 5 ones. We should have 5 terms, and we do. Okay. And you can clearly see when you look at up in here, you can see the sum of products. Well, let's look at the max term expression. With the max term expressions, I'll say this is the arrow. This will, I guess we need another little symbol. We will say it's this. So we're looking at that, we're looking at that, and we're looking at that, aren't we? So what are we going to have? We're going to have, we need to invert B, don't we? So I've got C or B that has to be inverted because it's a 1, or A, and then I'm going to AND this with the next term. Where's the next term? Right here. So I need to invert C, and I can OR it with a B or an A. And then I go to the last one. I need to invert what? C and B. So AND it with not C or not B or A. Okay. And of course this, you can see the product of sums. And even though this one is shorter, we'll probably see this a little more often because, like I said, we can go right into the Carnot map with that. But sometimes I'll talk about min-term expressions and max-term expressions, and that's what you got going on there. Questions with that? Well, a question comes up certainly in maybe this, well, this last case or even this case here. Could we have got something that was simpler? We want to try and use less power, have more reliability, so we want less gates. Can we get something that's simpler? So let's talk about some of our simplification techniques. The first one is just Boolean algebra. So some of the rules that we need for Boolean algebra. Let's talk a little bit about those. I think I got those here. So we'll talk about Boolean laws. And rules. Now you talk about this in discrete math? Okay, great. So we've got some laws. That A or B is equal to B or A. So the OR is commutative. And that A and B is equal to B and A. And I won't write this too often, but what this is really saying is A and B is equal to B and A. We usually just omit that symbol. So then we have, in terms of grouping, A or B or C would be equal to A or B ORed with C. So you can factor them. You can factor an AND. And you can distribute. So A and B or C would be A and B or A and C. So we have the distributive. And if you want to, you can, I guess this would be analogous to foiling in our base 10 system. A or B ANDed with C or D is going to be A and C, or A and D, or B and C, or B and D. So those are the laws. Let's look at the rules. And we saw a lot of these rules when we were going through the individual gates. Remember rules like A and 0 is equal to 0, A and 1 is equal to A or 0 is equal to A or 1 is equal to 1. We've got a few more of these here. A and A is equal to whatever A is. A or A is equal to whatever A is. Is that right? Yeah. A and not A is going to be equal to 0. A or not A will be equal to 1. We've seen most of these before. A, if I invert it twice, is equal to A. So a little confusing, but I think logically sound, like saying we're not having class on Wednesday. Yeah. Okay. And a couple others, a little bit, probably not as obvious as these, but if you sit down and think about them and go through some test cases, I think you'll probably believe them. So we could have A or not A and B, and that's going to be equal to A or B. And if you also have not A and B is equal to not A or B. Make sure I wrote those right. Yeah. Okay, so those are some of our rules and laws, and we could use those to just tackle problems straight on if we wanted to. We'll see that Carnot maps are probably a lot easier than this, but sometimes we have to use a little Boolean algebra even with Carnot maps to massage something to a point so that we could look at it with a Carnot map if someone's done some odd factoring or something. So once we get to Carnot maps, you don't want to forget this altogether, because it's probably going to be a test question on Boolean algebra, and also you'll still use it occasionally with Carnot maps. Well, I'll pull this back in once in a while, but let me move to another page and put up a problem then. Let's say that we want to reduce this minterm expression. So I'll start with this. We'll say that our output x is equal to not A and not B and C, or not A and not B and not C, or not A and B and not C. So I'd like to reduce this. Okay. So use Boolean algebra to reduce. So what can we do? Well, I've got not A and not B in both these front terms, or these first two terms. So could I write this as not A and not B and C or not C? Would you buy that? Of course, I just have to repeat this last term. Everyone's good there? Okay. What could I do with that? What if I look at, could I reduce this to, what's, C or not C going to be? Yeah, that's just going to be 1, isn't it? And so this really just turns out to be whatever A and B is, doesn't it? Okay, so I have that. And then this term's just going to tag along as I keep working through this step by step. So each term has a not A, right? So why don't I recognize that? There's not A and then not B, or B and not C. And this is where we could go and we could look at rule number 10, these ones here that are not quite as obvious as the others, and see if we can reduce this, and we actually can. This would be not A and not B or not C, which then we'll multiply back through, we'll distribute through, which is one of the laws, and say finally that our output is not A and not B or not A, not C. So I would say that that was our final form. So that's a pretty good problem. You did stuff like that in discrete math, is that right? Well, let's say what the motivation for this, if I were going to build this first expression here, let's say that I'm stuck with 2 input gates. So if I'm going to build this with 2 input gates, I'm going to have something like this. So I need to invert A. So I'll put an inverter here. There's A. And I need to invert B. There's B. And then there is C. So that's got that first term. And I need to take these two that are inverted. That's going to go into here. And this one that's inverted, I probably should have done that a little differently. And then put an inverter in this one. Okay, that's that one. And then what have I got with this one? I need A inverted, so I'm going to pick this up here. And I don't want B inverted, so I guess I'll pick that one up there. And I want C inverted, so I will take that off right there. And then I guess we'll stick with this being stuck with 2 inputs. So how many gates do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 gates?
How did you get from B not C to not C?
In which step here? Oh, this one? Right there? That was this rule down here, I think. One of these. I think if I numbered these, this would be what, 1 and 2, 3, 4, 5, 6, 7, 8, 9, and then these are a combination 10.
Well, where B and not C? How did you get not C?
Oh, going from here to here?
Yes.
It's this rule here. Let's see. So if I switch up my, let's see, I'm going to have to switch my A for B and my B for a not C. That should work. Okay. It's a fairly complex picture. What if I take this one and draw the circuit? What am I going to have? Well, with 2 inputs, and you might say, well, you know, you made this harder than you need to. You could use 3 inputs, but let's just be consistent here. We'll use 2 inputs. So I'd have A, not A and not B, so I'll have a couple of inverters. There's A, here is B, and then what do I need to have? Another inverter come off of this, and a C, and that needs to be inverted. So we got what, 1, 2, 3, 4, 5, 6, about half as many gates, less connections, more reliability, less power. Unless you're getting paid by the gate, this is the way to go, right? So simplification is important. This probably, for those of you that have done a lot of discrete math, is probably a fairly easy problem. Although it's probably not very, it's oftentimes kind of hard to figure out what your next step is. Let's try a method that's a little bit easier, or actually a lot easier. And we'll go back and start at square one with the Carnot map, but let's just apply the Carnot map to this real quick. So, and maybe I think I have enough room right here. Let's just say we have the Carnot map. And I'm going to have to go back and develop the Carnot map. How do you do it with 2 inputs versus 3 inputs versus 4 inputs? Well, let's just apply it real quick to this one. And our Carnot map would look like this. Okay, and here would be my not A, not B. Here would be my not A, B. Here would be my A, B. And here would be my A, not B. And then we need our last, which is going to be C. So I'll have my not C and my C. So if I go up here with what I'm given and I look at this, if I fill in the box, I have not A, not B, and then the C, so I'm going to put a 1 right there. That's the first term. And then if I look at this, not A, not B, not C, that would be this one, wouldn't it? And then if I look at this, not A, B, and not C, those are my 3 terms. Okay. And now I can circle 2s, I can circle 4s, circle 8s. So I'll circle that. So when I circle that, what does this first circle really mean? Well, what it means is C doesn't matter because I have a circle there when I have not C and when I have C. So I really, with this circle here, I can say that I have a term that is not A, not B, right? And then what's this circle here mean? Well, not C is apparently important, but what's not B really doesn't matter. Whether I have a not B or a B is the same, so I've got I can say that I have not A, not C. So I could write this then that my output is equal to not A and not B, or not A, not C. Is that the same thing we got? Yeah, it is. A lot easier. Okay. Questions with that? So Boolean algebra takes a little practice, and we need to go back and we need to properly talk about Carnot maps, but I think Carnot maps are going to be a lot more fun than Boolean algebra. So if there's no questions, let's go do that. So Carnot mapping, I guess starting at square one with this would be how to spell it. Carnot mapping. But developed by a name with the last name Carnot. He's working at Bell Labs, so it happened, I think, in the early 50s. So it hasn't been around that long. Boolean algebra has been around for hundreds of years. But the Carnot mapping technique has not been around nearly that long. You've seen already that we use it to reduce the number of gates, reduce the complexity, reduce the power consumption, reduce the initial cost, increase reliability. So it's a good thing. Probably came around when circuits were starting to get more complicated. The logical structures that we wanted to do with them were more complicated, and we wanted to try and get things as efficient as possible. Some of the combinations that we have is if you have a 2 input, you're going to have a Carnot map that looks like this. I don't know that we'll use too many of these, but you'll have not A, and then not B, and B. And I always just stick with this designation. A lot of times students will try and mix it up, and they do it at their peril. I would stick at always having not A, and then not B, and B, and just go with that. Sometimes students in preparation for the exam on this will come up with Carnot paper. They'll just put a bunch of Carnot maps on a piece of paper, and then they can just fill in the ones very quickly and don't have to mess around with that. As you've seen already, if you have a 3 input, you'll have something that looks like this. Where we have not A, not B, not AB, AB, A not B, and then not C and C. And probably the most common we're going to look at, there's more, you can go with more than 4. You'll start to stack the Carnot maps on top of each other. We're not going to do that. We'll max out at 4. So we're going to have not A, not B, not AB, AB, A not B, and then over here we would have C, D, and not CD, and then CD, and C, not D. So while the variables, I mean, you might not be using A, B, and C, D as your variables. Those could change, but I always keep the nots in that particular order. That seems to work well. If you start mixing up this, you have to mix up that. I just probably wouldn't do that. So let's, then what you're going to try and do is you're going to try and circle. Anytime that you can get, like we did on this last one, that you can get a circle with 2 ones, you're going to take that. If you can get 4 ones, that's even better. We'll just do a variety of examples and realize that it's really maybe not a Carnot map, but a Carnot globe, in that this point and this point and this point and that point are really all the same point. So if we end up, for instance, in this case with a 1 in each one of these corners, we actually have a group of 4. So we'll see that when we go through it. Let's go to the 4 input ones. Let's try another 3 input. So let's say that we have something like this, not A and B, or not A, not B, not C, or A, B, not C, or A, not B, not C. That's a good one. Let me do these first. I think they're probably going to be a little easier. So I'm going to use the 3 input, right? So not A, not B, that's going to put me right here with not C, so that's going to be the first one. Then A, B, not C, that'll put me right there. A, not B, and not C, that puts me right there. And then this one is kind of interesting. If I look at that one, I could say that, what? C doesn't really matter, right? So we could say that it's not C or C, couldn't we? So what we really need to do is we really need to put a 1 there and there. So this gives 2 1s. Okay. So because I had not A, not B, I had to put this one here for not C, or that one for C. So how can I circle this thing up? Well, I have a nice group of 4 there, don't I? And I have this group of 2. So with this, I could say then that the reduced one is going to be, what does this vertical circle of 4 tell me? Yeah, A and B really don't matter. So I would just have C naught, or, And then this one is really just going to repeat this one here, not A and B. So there wasn't any simplification on that term. But in terms of gates and whatnot, tremendous simplification. Questions with that? Now, like I said, I don't know that we'll do any of these 2 inputs. We've done enough of the 3 inputs. We're going to do a lot of these. So probably for the rest of this lecture and maybe into next lecture, we'll look at some of those. So if there's questions, let's head that way. So let's say that I want to use a Carnot map to reduce this expression. The output is not A and B, not C and D, or A, not B, not C, D, or not A and not B and not C and D, or A and B and C and D, or A, B, C, D. I guess I got one more here. This is a long one. There we go. Okay, so if I build a Carnot map for this, and we'll do quite a few examples, and I'll try and get examples that come up with different scenarios. It's kind of hard to learn when I say, well, if you have a 1 here and here, you do this. It's probably a lot easier. We'll just carefully select our examples and see those come up as they come. Okay, I think I'm okay on that. Like I said, a lot of times people will just make themselves some Carnot paper, put that on a piece of paper, and make a few copies of it, and then you move through the test a little faster. You have to do this kind of business. So let's see, this first term, where am I going to be? Not A, B. So I'm going to be in the second row. Not C, D, second column. Then the next one, A, not B, so I'm going to be down here, not C, D, right here. Third one, not A, B, so I'll be up in that top column, not C, D, right there. Fourth one, A, B, so third row, not C, D, second column. And lastly, where am I going to be? Whoops, no, I have a couple more, don't I? 1, 2, 3, 4, yeah. So not A or AB, and then not CD, so I'll be right there. And then lastly, ABCD right there. Okay, so I'm trying to do multiples of 2, so 4 is a multiple of 2. That works. 3, that's not a multiple of 2, is it? So I can do a 2, which is a multiple of 2, and a 2, which is a multiple of 2. So that's the best I can get. Now, if let's say that you don't see something and you circle 2 4s, you'll probably still get an okay circuit. It'll work. It's just not going to be the simplest if you pass up a 4 and circle 2 2s. So what do we learn from this? This large vertical circle of 4, what does that say? A, B really aren't playing in this thing, are they? We just have not C and D. Or then if I go to this one, what's that telling us? A, B, and not C. Great. Or this last circle is A, B, and A, B, and D, right? So if you were to build this, I'm not even going to belabor making that first one out of 2 input gates. It would be ugly. Okay, you make the next one to be a lot easier.
Hey Mark,
Yes,
can you explain how you get the ABD?
ABD. Oh, this last one.
Yeah.
Okay, so with this circle here, I know that it's in the AB, so AB is going to be involved. But because I have a circle here and here, I'm looking at essentially these two, and what's repeated?
Oh, okay.
D is repeated, but C changes. So it looks like C really doesn't matter, because whether I have not C or C, I still have a circle there.
So you're just looking at what's similar.
Yeah.
Okay.
What's similar remains. Other questions? And this may be one of those that going back and looking at the video is maybe well worth the time to just go through the process on these. Let's try another one. So we'll have B, not C, not D, or not A, B, not C, D, or A, B, not C, D, or not A, B, C, D, or A, B, C, D. Yeah. Okay, so we'll come up with our Carnot map. Okay, so let's hold off on this one. That's probably a more difficult one. We'll just do these others. I think we should be pretty comfortable with that. Not A, B, not C, D, so I'm going to be right here, aren't I? And then this is A, B, and not C, D, so I'll be right there. And then this one is not A, B, not A, B, then C, D, so I'll be right here. This one's A, B, C, D, so I'll be right there. So the first four give us those four. And then this one's actually going to give us two because it really doesn't matter what A is, right? So where do I have a B that's not inverted and then a not C, D? Well, I'm going to have that right there with a not A, and I'm also going to have it again with an A, right? Okay. So this term gives us both of these. So it's not uncommon for a term that seems simpler, only 3 terms there, to give us 2 in the Carnot map. So I want to do multiples of 2. Well, 4 is a multiple of 2. Actually, maybe I shouldn't say multiples of 2 because we could do 6, but you can't do 6, so we want powers of 2. So we want to have 2, we want to have 4, 8, and so forth. So how should I make the next circle? Should I do this, what do you think of that one? You could, but you're not going to get the most simple. The most simple is going to be do something like this. There's no requirement that they don't overlap. So now if I look at this first circle, what does it teach me? That A doesn't matter, right? So I'm going to have B, not C. Or, and what's the second circle tell me? Again, A doesn't matter, so I'm going to have B, and then up here it looks like C doesn't matter. So a pretty significant simplification there. Yeah, so I think I said before multiples of 2. I really should have said powers of 2. So we want 2, 4, 8.
So when creating these columns, we just have to look at our concrete pillars and use all the values.
you're good. Once in a while, you get one over here that's just hanging out on its own, and we're going to have an example coming up. You just have to put a circle around it and deal with it. You just won't get any simplification there.
So we're just going to have to achieve it as well.
What's that?
We're just going to have to improve it.
Yep. Yes.
So if you would have one in the red, it would be like A.
Yeah, if you had this guy, you would just have another term in there that would be not A, not B, C, not D. You just tack it on there. And we're going to have that example coming up. I mean, the bad news is you might get a little tired of this. The good news is we're going to show you an awful lot of combinations. Let's try a few more here. What did we do? 13 pages last time? I don't know, maybe we'll get to that this time. Now, this looks like this could be fun.
I don't think we have the same idea.
Hey, when you base it on Boolean algebra, this is looking like a blast, isn't it? Yeah. Okay. So. Okay, so let's put this into a Carnot map. Okay, is our knots in the same order? Yep. Okay, so let's see. The first term, yeah, some of these are, this is the only one that's going to be reasonably easy, right? The rest of them, I'm going to end up with a lot of ones in this thing. So if I look at this, where do I have not A, not B? That's going to be the first row, and then anywhere that I have not C. There's a not C, and there's a not C. So that's first term. Then the second term, I'm going to be at a not D. Where do I have not D? Well, there's an A and a not CD. Here is another A and a not CD, right? And then up here, A and not B. A and not B. Where do I have an A and a not B? I have it here. And when we put a 1 on top of 1, you don't put this over here. You don't get Roman numeral 2 or something like that. It's just right on top of it. There's no more points on that. It's just there. But you do get that. Okay? And that's from this term. Then we got the one here that's easy. AB, C not D. That'll be this one. And lastly, we go over here, not A, not B. And then I have C, so I would get one here and one here, right? Yeah, that's good. This is good. So how can we do this? I told you before that this point and this point and this point and that point actually all touch. It's kind of wrapped around. It's a Carnot globe rather than the Carnot map. So I want to get the largest ones I can. So what I propose is that we look at this one and this one, which would give us 8, right? Because remember, we can go, and I said multiples before, I should have said powers 2, 4, and 8. We don't do 6. And then you might be think that you certainly wouldn't want to just circle this 1. It's not going to be as simplified. If you said that, well, I could put a 2 in here, you're thinking right, but not far enough. Remember, we could do what? We could do something like this and get a what? A 4. So now we've got this thing really simplified. What does this, the one of 8, tell me? Well, let's see. A doesn't matter. And C and D don't matter, so all I have is not B, right? And then what's this one down here in the lower part, the one of 4, tell me? A matters? And not D matters, right? So we got tremendous simplification on that one. Questions with that? Now, had you just done a circle here, you would have got more terms. It would have given you the right answer in terms of logic, but it would be just like an intermediate step in your Boolean algebra. So if you want the most simplified, you got to go for the bigger circles. Yes? Bottom right here?
And that's the only one you have.
Oh, if this was the only one you had?
And the bottom left.
Okay, so let me... Let's see. So you said I had a 1 here, and where else did I have one? Right there? Yep, you could.
What if you move both of those on the up one?
You still would. Yes. Which, for instance, if I had this, I would still just have this. Yep. You want to think about it going all around, like wrapping it around a rubber ball or something. Not just the corners.
What if you had
Diagonal. Oh, this and this. I don't think you can do diagonals. I know you can't do diagonals like that. I don't know about the corners. I'd have to play with that one. Yeah. But they'd still be diagonal like this. I think you're thinking okay, but when you get it wrapped around, you've got this corner there, and they'd still be like that. And we can't make those. Okay. So good questions. Let's finish up with one more, or maybe we'll at least get it started. We may not finish it. Let's say someone gives us something like this, that our output is not B and CD or not C and C not D. So let's say someone gave us something like that. And I wanted to simplify it. This is one of those where I'm probably going to have to do some Boolean algebra first, because I don't have a min-term expression. I can't go directly into a Carnot map. So I got to try and get it tidied up so I can get into a Carnot map. So let's see, what can I do? I could distribute this through, right? I would have not B and CD, or not B, not C. And then what I'm going to have that one. There's some idea. There's where that sign comes down. And then I'm going to have, I'll repeat this here. And then inside here, I got away without showing you De Morgan's theorem, didn't I? Yeah, no one called me on that. So De Morgan's theorem. Maybe I'll put that up here. De Morgan's theorem says that if I have A or B and I invert the entire thing, that is equal to the inverse of A ANDed with the inverse of B. Conversely, if I have A and B and I invert the entire thing, that's equal to the inverse of A ORed with the inverse of B. Double check that. I don't want to write down the theorem incorrectly. I think we're good. Okay, so, and this is really what's responsible for when we were looking last time at the gates and how it was drastically different what I got when I put the inverters on the input of the gate versus the inverters on the output. If I put the inverters on the input, I have something like the right-hand side of De Morgan's theorem. If I put them on the output, I have something like the left-hand side. So that's how we could really change those things up, whether we put the inverters on the input or the output. So these, I probably should have listed those when we were going through the Boolean rules. We lucked out in that problem and didn't need to use it, so I didn't get motivated to lay those out. But we need them now. So what do I have? It looks like a job for De Morgan's, the first part of that, right? So could I rewrite that? What am I going to have here? This would be this one, so I would just say that this is not A, not B. It's the implied and between those, or A, B. Is everyone good with that? So then we could keep working on this. We'll have not B and C and D, or not B and C, or as I factor this through, I'll just put it in alphabetical order, not A, not B. I keep anding here, C and not D, or A, B, and C, not D. Now, could we do something with that? Yeah. Now we can go to the Carnot map. Okay. And that's a good stopping point. Maybe we'll come back and repeat this so we have a little touch up on Boolean algebra. Next time we'll put it into a Carnot map. We'll reduce it. We've got a couple more Carnot maps to look at to make sure that we're comfortable with different combinations. And then we'll look at a physical situation. Let's say that we want to build a monitoring system for an engine or something like that, and we have these logical switches. We'll talk a little bit about how we can make those switches, instrumentation and whatnot. Put the Carnot map on that, and that's going to really finish up most of our digital work in this class. So on Wednesday we'll be able to easily finish that, and we'll come back then next week and get started with the rest of the term. So if you're wondering in the scheme of things where we're going to stop just before moving into flip-flops. So if you're reading along in Shams or kind of following along, we are not going to do flip-flops in here. So I guess that does it for the day.